So I remember when I was when I was doing my undergrad at MIT, you know, I was pretty immature in a way, you know, but I had a lot of fortunate opportunities to learn general relativity and quantum field theory, which are both grad classes. But I just wanted to get as far ahead as possible. And you know, as a student, it's kind of like, why can't I just naively quantize gravity like a quantum field theory?
Yeah, like
and
just go straight
do it,
for it, right?
Just do it, right? And they run into these infinity problems, and you know, these infinity problems are nothing new in quantum field theory. That the whole development of quantum field theory took a long time to figure out how to deal with these infinities, and they figured out how to do it for 3 of the forces. So there's electromagnetism, there is the weak force, and there's the strong force, and all of these 3 are put into what's called the standard model of physics. So we have this model of physics. It's a well-defined quantum theory. They all play nicely together. We have a decent understanding of how to calculate a lot of things in this theory. However, we don't seem to have any way to add in gravity into this framework. And it seems like general relativity is this huge theory for gravity. So how can we relate quantum field theory and general relativity? It's a huge question. And most people say it can't be done. That's kind of the consensus right now, in some sense, that quantum field theory should just be an effective field theory. It's not fundamental, but it turns out that you can actually calculate some things in gravity, treating it as an effective quantum field theory. So this is actually why I came to UCLA to work for Zvi Bern to get my PhD, because that's one of the things he figured out. So the force carrier of gravity is called the graviton, right? And the force carrier of the strong force is called the gluon. So my advisor figured out a way to actually calculate graviton scattering from gluon scattering, which showed that there is a possibility on how to calculate these things. However, it still is a little bit problematic. So you can calculate, miraculously, you can actually calculate a quantum correction. So the first quantum correction miraculously turns out to be finite, which is a huge mystery for a lot of people. They don't understand why it could be finite or should be finite. But I mean, that's very important evidence that something can be done. Now the issue gets worse when you go to further quantum corrections, but let's just stop there for a second. So it turns out that when you try to bring in matter and have that interact with the gravitons, you can't get it to work nicely. You're going to run into infinity problems. So it's still an issue. We can't actually calculate quantum gravity as a quantum field theory when we introduce matter naively. But it seems that by studying these Einstein-Cartan geometries, it gives you a natural UV cutoff. So UV just means high energy. It's just a term that we use. So we're having these particles, they're scattering. You know, Feynman rules say that we need to sum over all possible paths. Well, that's his formalism. So we're using this and we're integrating over momenta. So we would integrate, they could be anything, 0 to infinity. But it seems that if particles had a finite size, then that would actually limit how close an object could get to it. And due to position and momentum uncertainty, it would actually give you a UV cutoff if the particle is actually not a singularity, but rather had some structure. And actually,
geometric structure,
I mean, there's this paper I saw in 2011 that said that if you study our, that it could be a torus. But they didn't even write down the mathematical solution. But there's this other paper that seemed to suggesting that Einstein-Cartan theory has this UV cutoff. So, you know, the question could be asked: what if we just try to naively compute, you know, quantum gravity in this Einstein-Cartan theory? And a lot of people will say, well, it's not general relativity, but it's very close. It's very similar. And the only thing that going to this Cartan geometry adds into the theory is this thing called torsion. And this torsion doesn't even do that much. So most physicists say it's not useful, but it tells you how the quantized spin of these different particles actually interact. So it seems useful. And it's really interesting because in Garrett's model for when he uses E8, what he's trying to do is to have a way that describes all of the particles and all the forces, including gravity. And what's interesting is his formalism is developed on Cartan geometry. So, you know, in this sense, it seems quite natural that E8 maybe something like what Garrett's doing. I mean, obviously he hasn't figured everything out, but you know, it's suggestive that there's something actually here, and there might be some naive path ahead where we could actually maybe compute some things.
Yeah, Cartan actually, he's the one that classified these simple Lie algebras. So it's funny his name's popping up multiple times. So there's something suggestive there. Well, at least at the name level. And you were saying that some people approach Cartan geometry with a torus, which is the donut shape, right?
Yeah.
Do they ever approach it with, say, just a ring, just a circle? Have you seen that done as well?
Yeah, so actually, you can even get the ring, you can get a ring singularity in general relativity even. So you can study black hole solutions, and these are like singular objects. So, you know, I can have some Schwarzschild metric that describes black holes, but what's remarkable about this solution is that if you're far away from the black hole, it even works well for any spherical object. So if we have some sun that, let's just assume we had some huge planet or some galactic object that's stationary and not rotating, or it could be moving around but not rotating, it effectively from far away, it can be described as a black hole, which is kind of interesting because, you know, we also see that it seems in elementary particle physics, you know, particles, we think of them as being singularities, right? So, but what if you rotate the black hole, right? What happens? And that gives you a Kerr metric, and in some instances you can get a ring singularity from that. So that's pretty interesting.
So another topic that arises is Hawking radiation.
Yeah.
So what if we study, right, these large black holes, and we do it in a theory where it's not general relativity, where there's a little more structure, such as in supergravity, right? And we study the ground state, I guess, of this Hawking radiation, right? this remnant of what may be the extreme case, or the limiting case of this Hawking radiation. So that's the extremal black hole.
After it's all radiated
yeah,
away,
what do you think?
What's left over?
Yeah. What are your what are your thoughts about that extremal black hole that could exhibit these higher symmetries, right? It could be an exceptional symmetry.
Right. I mean, I think extremal black holes would be interesting to study because, I mean, it seems to be this sort of reduced element, right?
Right.
In some sense, it's, you know, you might be able to connect them to elementary particles eventually. I don't know yet. I mean, these are open questions, but, you know, we know that a particle itself is stable, so it doesn't radiate.
Yeah.
So it's interesting to look at these exotic theories of gravity that have extremal black holes, but they're not really putting in the matter content yet with that. So it's still unclear how it all comes together, but.
Yeah. And you mentioned, well, MIT, going back to that, I sent you a paper by Frank Wilczek. And he was identifying, or there's a certain regime in which you can identify these extremal black holes with a particle, right? He said.
I didn't even.
Yeah, I don't know if you took a look at it, but that could be
I forgot about that. I just was swinging this.
Right.
So I guess I did actually hear that before, right?
But you've browsed it, right?
Yeah,
the abstract. Okay, so given that kind of connection, right? If an elementary particle, if there's really certain regimes in which an elementary particle and a black hole are indistinguishable, then perhaps that may be a route into which unlock the secrets of this this conundrum between general relativity and these quantum field theories that are based on Yang-Mills.
And it's very interesting because for my thesis right now, I'm actually studying various different radiation. It's not Hawking radiation, it's not quantum mechanical radiation, it's all classical, but there was this paper that was found where they're actually able to essentially make this double copy mapping between like what you would just call a quark, essentially, and a black hole. Like, you know, the solutions of quarks create, you know, they're the source for gluons. They're the source for the strong force, right? And black holes, you know, they're these fundamental particles, or not fundamental particles, I shouldn't say that, right? But they're just these objects that create gravity. So they're similar in that sense, and the solutions map up within this double copy framework completely.
So what if one it just envisions perhaps, say, a black hole in color space, right?
So I mean,
would that be indistinguishable, say, from like a quark with the strong force?
We know a quark has a mass, right? So what is a particle? You know, if you're going to study the gravitational interactions of a quark, the first approximation you would take is to say it's a black hole. If you're far away from it, you know, we use black holes solutions to model the sun, but we, you know, I mean, there are black holes out there, you know, in our galaxy and stuff. At the center of our galaxy, there's probably one, right? But do we say our sun is a black hole? Not really, but the mathematical solution can be used within a certain approximation.
Right.
So if we stick to these approximations, they give us these analogies, right? So it might not turn out that, you know, an elementary particle is a black hole. That might not be a true statement.
Right.
However, it might be a decent analogy, and it seems that there are approximations that we can make that connect the solutions. So it's intriguing for that reason.
What if one instead studies the charge space of these tiny black holes?
Well, you can take a black hole and you can just study, okay, we have a black hole that has some mass. You can say, what if I have a black hole with charge, right? You can do this. And you can do this in the theory of general. So, I mean, it's not commonly studied in great detail, but you could, what if I put a color charge in there?
Right.
There's no reason why you can't do that, right?
Yeah, so we can envision, say, just like you were saying, a black hole with some kind of SU3 symmetry, perhaps, some little extremal black hole. So in that case, we can get very familiar structures in quantum field theory from some black hole object that someone has really.
So then it would be interesting to study. I mean, if you were to look at these extremal black holes, okay, we have these different quarks. That would be the real key. Can you somehow, how do we figure out, can you study somehow study these extremal black holes and then identify the elementary particles that we see, or would you just see arbitrary particles? Like, you know, the electron has a specific mass, it has a specific charge.
Yes.
Why is that? These are still questions. We don't understand why things have the mass they do fully yet. So, you know, within this context of the extremal black holes, I guess you could imagine, well, I guess extremal tells you that the charge, it gives you a charge to mass ratio, right?
Yeah.
So you could consider other black holes that are not extremal that have various charges and masses, right? So I think that's the big key. The big question that we're still trying to figure out is, you know, why do we have the particles that we have? And why is always a difficult question to answer, but what I find interesting about, you know, Garrett's model with E8 is that he has this structure that is just very algebraic, and it seems to naturally give you all of these charges that relate to the particles that we see and the forces. So, I mean, you know, I think there are a lot of work still needs to be done to really investigate all these avenues. It's not a finished like model per se, you know, but these are suggestive ideas that we should all be thinking about.
Yeah, and speaking of the black holes, there's this concept of a Freudenthal triple system. So it's this mathematical structure that allows you to study these black holes in supergravity. So you're well aware of research by Alessio and Sergio Ferrara here at UCLA. So these mathematical structures were based on these octonions, right? So if you take octonions and you make matrix algebras over them, and you make these extended algebras over them, then you essentially have a Freudenthal triple system. So E8 is usually thought of as an object whose symmetry is itself, E8. Okay, now that's a linear way of looking at it. If you take a nonlinear way of looking at it, you can look at E8 as the symmetry of a 57-dimensional object. Okay, so what it amounts to mathematically is this 56-dimensional space with an extra coordinate. Okay, so it seems a little odd at first, but later on we can talk about it when we get to a board, and I can show you how you can diagrammatically write this, express it in terms of a projection of E8 along an SU3.
Wow.
So we go back to that diagram. So it makes it super simple, almost too simple.
So, and going back to what we're saying, I mean, we know that space-time has to be emergent. So if we're going to study quantum gravity, it seems that we need some object, some abstract, maybe geometric notion that has space-time emerge at the same time as the particles. So, you know, in order to have an interaction, in order to refer to a length, in order to refer to space, you have to have an interaction. And, you know, you can't just have any interaction, you have to have physical interaction. So it seems that the structure of space-time itself could be intertwined with the emergence of what the particle identities actually are too. So I find this to be really interesting in that way.
Yeah, like you're going back to Einstein's original picture of an interaction-based picture, right?
Yeah.
So there's this notion of events.
Exactly.
So how do you define coordinates, right? Well, you base them off of events, which are interactions. So if you're looking at it from the quantum field theory perspective, then you would have to describe this interaction, and this gives you an event. So we're accustomed to this notion of fiber bundle. Okay, so this notion of fiber bundle came up where you have a base, which is space-time, right? And you have certain fibers attached to each point in that space-time manifold.
Right.
Right? So we can ask, okay, if we have the standard model, for instance, right? So we know the standard model has SU3 cross SU2 cross U1 symmetry, modulo some discrete symmetry, which are 6 points, okay, some Z6. But overall, we're looking at these unitary groups and asking, okay, so these are symmetry groups of what, okay? So then that takes us back to this notion of projective space, okay? So SU3 ends up being the symmetry group of a very particular projective space, which is the complex projective plane. It's CP2. Okay, so we can think, okay, can I do the same for SU2, right? So yes, that will describe rotations or isometries along an SU2. I mean, sorry, along a sphere.
Yeah.
It's actually a sphere, and you can think of it as a pure state space, right? In the case of quantum mechanics. So you can say, okay, well, if I have this space-time manifold, it's not convention, it's not convention to imagine these projective spaces as fibers coming from the base manifold, but mathematically you can think of it that way. So if we're looking at three of a Cartesian product of three Lie groups, in this case, we can have a circle which has the symmetry of the U1, as the U1.
Right.
We can have a sphere that has the symmetry as SU2. And we have the CP2 space, which gives you the SU3 for the color symmetry.
Yeah.
So it's almost like we have a multi-fiber coming out of this base space. So all we're asking is if there's a certain way to unify all these fibers so that it's just one object, right? Instead of a Cartesian product of three objects. So it doesn't seem too unnatural to expect that we could do that. So I usually like looking at Garrett's way as similar to not only producing the fiber bundle, it's a priori not even a fiber bundle, but we can have this E8 object whose we could think of it as a certain grading, right?
Right.
Which is a different slice, a certain slicing of E8, which gives the base space as well as certain fibers, right? So the question is, what's the proper way to slice E8 to make it work, right?
Yeah.
If it can work at all, right? So that's an open question in this case. But using the intuition from supergravity, right, these mathematical structures that are useful in studying these extremal black holes, it's possible to take that and bring it back to the study of what Garrett's doing and actually unite them. So that's what I'm interested in these days. And I was able to study that along with Alessio Morani and Piero Truini, who came up with this so this diagram you have on your shirt, okay, so this is a certain projection of E8 on a plane, but you can project along an SU3 and turn this into a star-like shape. That makes everything totally obvious when it comes to these extremal black holes, okay, but mind you, these supergravity theories are a different theory, right? We have a notion of supersymmetry in there, and normally we don't relate them to something as practical as what Garrett is talking about, right? Because in here he's identified Higgs particles, he's identified quarks, the leptons are the charged leptons and the neutrinos. So with this new diagram, it seems a little more easy to get in there and start identifying the particles and perhaps relating that structure to these extremal black holes. Right. So that's essentially, I mean, it's a nice way to think about these things. We go back to those guesses where an elementary particle and a tiny black hole aren't too much different.
Very similar.
Right.